Welcome all of you. Since last 2-3 classes we have been discussing about analysis of the heteronuclear spectra of varieties of nuclei like fluorine, phosphorus, boron, silicon, mercury, varieties of examples we took. And we knew how we can extract the coupling, especially for abundant spin, phosphorus, fluorine, if you do, how to get the coupling of the abundant spin. And from the satellites we could get the coupling between abundant and rate spin. And I took the example of boron. We have two isotopes, boron 10 and boron 11. And boron 11 is going to give you 4 peaks of equal intensity because of spin 3/2. Boron 10 gives 7 peaks of equal intensity when it is coupled to spin off nuclei like proton, carbon or fluorine like that. That's what we observed. And we could get the coupling between boron and proton, fluorine, etc. Similarly, silicon NMR, we took the example of couple of molecules. We could see 1 bond silicon coupling, 2 bond silicon coupling, how the spectrum can be complex. We can get the coupled proton coupled silicon spectrum, proton decoupled, and we can get when we do proton decoupled, silicon coupling to other dilute spin like carbon, we could get carbon silicon coupling like that. So many such examples we took. And we can go ahead with few more nuclei. Of course, there are several isotopes in the NMR periodic table. All elements and all examples we cannot take. Few more examples which you routinely come across, I am going to discuss. Because all these things, when you do with the bio NMR, chemistry, in the chemical applications or material science, we come across these things. So I am going to take few more examples of some standard nuclei. Okay, we will start today with what is called nitrogen 15 NMR and nitrogen 14 NMR. Nitrogen 15, of course, is spin half nuclei, abundance is 0.37%. Nitrogen 14 is spin 1, abundance is large, 99.63%. So, interestingly, this is quadrupolar nuclei. Very rarely, we are going to get sharp peaks there. But we will see what to do. I am going to look at the NH14N spectrum of NH4Cl. I am looking at 14 NMR coupled to equivalent 4 protons, like we saw, BH4. What is the type of spectrum you are going to get? 4 protons are equivalent and coupled to spin 1. Doesn't matter whatever the spin of this coupled nuclei, but these are chemically equivalent 4 protons which spin half 2 Ni plus 1 if you apply 4 into half into plus 1, you get 5 peaks. Exactly, you are going to get 5 peaks. And measure the separation. This is going to give you 14N and 1H coupling. Remember, it is one of the rare examples because nitrogen 14 usually is a quadrupolar spin, very broad, and it generally broadens the signal. But here is an example. This is in NMR jargon we call AX4 spin system because nitrogen proton are heteronuclei, 4 equivalent proton, we call it as AX4 spin system, and we are looking at A part of AX4, it is going to be a quintet like this. And directly we can measure the separation and get the nitrogen 14 proton coupling. Of course, we can also look for the 15N NMR of a simple molecule like ethylene diamine. You see, remember, taking the nitrogen 15 NMR spectrum in natural abundance is a fairly difficult task because nitrogen 15 abundance is 0.37%. Very difficult to see that unless you are labeling the system. And also further, it has a negative magnetic moment. You have to do a lot of NOE, etc. I will discuss later for enhancing the signal. But usually, nitrogen 15 is, although the spin off nuclei, fairly difficult to detect because of its sensitivity. But nevertheless, we can still do it. And this is an example of ethylene diamine in CdCl3. And this is a spectrum. There are 2 spectra here given. One is proton decoupled, other is proton coupled. In the case of proton decoupled, you can clearly see we are going to get a single peak because there is a symmetry here. There are only 2 nitrogens here, both are chemically equivalent. So, you are going to get a single peak. But how many couplings you can get tough? If you want to look for the coupling, you can have 1 bond proton coupling, okay, and then this CH2, this 2 bond, and this can also have 3 bond coupling. So, you have 3 different couplings if you look at the proton coupling. And there is also proton coupled spectrum given here. And this is a very funny pattern of quintet. Why do we get this quintet? This can happen only when this is also equivalent, these two are equivalent coupling, triplet of triplet. It's so that some of the lines are overlapped. We have taken the example of in the proton spectral analysis of the multiplicity pattern. It is triplet of triplet so that both the couplings are equal somehow. As a consequence, you are going to get a quintet. You ask me a question, what happened to one bond coupling? Why I am not seeing that? One bond coupling has to be large in this. But in this case, one bond coupling is absent due to rapid exchange. We don't see one bond coupling here. We are seeing only 2 bond and 3 bond coupling, almost they are equal approximately. As a consequence, the nitrogen 15 coupled proton spectrum, proton coupled spectrum is a quintet for this molecule. Of course, usually if you look at the nitrogen 15 NMR spectrum, they are very simple. Because in a given molecule, there will be few nitrogens, 2 or 3 or 4 nitrogens will be present. Unless you go to a protein etc., there are too many amino acids present, then each amino acid has an NH proton, you will have lot of nitrogens. If you go to a big protein, there will be too many nitrogens. But in a small organic molecules, simple molecule like this, hardly there will be 2-3 nitrogens. So we have 2 nitrogens in this molecule. This is a proton decoupled NMR spectrum here of nitrogen 15. You are going to get only a doublet. Very simple. You got a doublet. Very easy to interpret which and which. Okay. We will go to tin NMR. Tin is also another interesting thing. Tin has 3 isotopes. Tin 119, tin 117 and tin 115. All are spin off. All the isotopes are spin off. All are NMR active. But only thing is all are negative magnetic moment similar to nitrogen 15. Doesn't matter. As far as the detection is concerned, let us not worry about it at the moment. Tin 115 is very low natural abundance, 0.34, similar to nitrogen 15. And sensitivity is 0.68 compared to carbon 13 if it is taken as 1. So practically we can ignore tin 115. We will worry only about 119 and 117. And 119 and 117 have almost equal natural abundance. Very interesting, you see. If almost 7.7 and 8.6, take as both equal abundance, 8. Sensitivity of 17 is 19.9, about 20, this is 26. These are all some information to analyze the tin NMR spectra. Let us analyze the tin NMR spectrum of SnH3 minus and its deuterated analogues in liquid ammonia. You will remember this statement tells me deuterated analogues. So I take SnH3 minus is my molecule. Its deuterated analogues means we do not know how many deuteration is possible. It can be SnD3, SnH2D, SnHD2, SnH3. All isotopomers are possible. Okay. So this spectrum is a combination of all those things. Now our job is to identify which is which and analyze it. Of course, if you carefully look at it, there is a lot of isotopic effect here. You can see that chemical shift, isotopic effect is such that peaks have been drifted quite a bit. Look at this one. This is taken from the paper Chemcom in 1987. First of all, SnH3 you consider. How many peaks you expect? If you look at tin NMR, tin 119 we are looking at. You will get only a quartet because all the 3 protons are chemically equivalent. So it will be a quartet of intensity 1331. This I would say is SnH3 minus without any difficulty. Okay, what are the other combinations we can think of? Sn D2H. That's also possible. Okay, we will see what are the possible combinations, what are the isotopomers, where we can assign each of this. I would say SnH2D. Why did I say that? Remember, these 2 protons split this into a triplet. It is a triplet here. Center of this to center of this, center of this, 1:2:1 triplet. And each lane of this triplet is split because of deuterium, which is spin 1 into 3 lanes of equal intensity. See, this is what you got. I would clearly say this can be assigned to SnH2D minus. Whatever the next one? Next one I would say this is SnHD2. Why? Because this is a doublet because of proton coupling. So tin will split into a doublet, and then each lane of the doublet is split because 2 equivalent deuterium into a pentet like this. 1, 2, 3, 2, 1, which we saw earlier. 2 deuterium equivalent, when it splits spin off nuclei, it will make it 1, 2, 3, 2, 1 pentate. That's what you get. First, this doublet is because of SNH coupling, and each of these pentate is coming because of deuterium coupling. So that's also possible. We could analyze. What is the next alternate possible next isotopomer we can think of, or next analog of this molecule? Next is SN-D3, no proton at all. Then how many peaks you expect? You expect in that. Put it into your equation, 2Ni plus 1. So I is equal to 1. So 2 into, there are 3 deuterium, 6 plus 1, there should be 7 lengths here. All are not resolved. All are not clearly visible. It is a poor signal to noise ratio. In reality, if you get a good spectrum, this should give rise to 7 peaks. And I would say this is because of SN-T3. So all the big groups of peaks can be easily assigned to different analogues of SN-H3. This is a tin 119 where you get proton coupling and proton deuterium coupling, both are present here. Okay, an example, and you can see clearly the isotopic effect on the chemical shift is enormous. This is for H3 and replace one of the proton by deuterium, and this has shifted by this much. And if you go in the ppm, approximately about 3 to 3.2 ppm it has shifted. Huge shift in the chemical shift. So this is because of isotope effect. All right. We will go to the another example of a molecule, tin 119 spectrum of this simple molecule like this. Look at this molecule. And every line here is a genuine peak. And this group is expanded, this group is expanded here, this group is expanded here, these are peaks. And there are only 2 tins here. They are non-equivalent, 2 tins are there. And we are getting so many peaks here. How do we analyze this? Every peak has to be assigned. So how do we do that? We will start with this simple example, analysis of the tin spectra. First, these 2 individual peaks can be there. Okay, and possibility 1, both can be individual for tin, 2 signals for tin 119 in 2 different environments of A. That is, it could be 115, let us say. That will not couple at all. There is no coupling between these 2 individual spins you get. That is a possibility. So both will give individual peaks here, and it pertains to 2 different molecules. Tin 119 for one when it is A, one it is B. There are 2 peaks, both the peaks corresponding to possibility 1 for A, 1 for B, and from 2 different molecules. So strong peaks we can assign. There is no coupling with anything else. That is one possibility. All other couplings are ignored. Now let us, for this I have already discussed, just because in future next analysis of this molecule we come across AX spin system. And the AX spin system is there, we get 4 peaks, 2 for A and 2 for X, that we have been discussing. This separation gives you a doublet. It is symmetric, it is A is coupled to X, X is coupled to A, interaction is mutual. So both will be doublets, each will separation of the doublet in A or X will give you J coupling between A and X. With this we will consider what is the possibility. There is a possibility molecule contains one 119, others 117. There are 2 isotopomers. But remember, both of them abundance I said 7.6 and 8.6, both of them are equally abundant, both of them are spin half. There could be a coupling between them. We cannot stop that. And both of them may have a different resonating frequency. Tin resonating frequency 119 and 117 are far apart, megahertz away. See, frequency here it is written, you see, they differ by 8.3 megahertz. And coupling is very small. So they are weakly coupled AX spin system. And a 500 megahertz spectrometer, if I record, chemical shift is almost 8.3 megahertz separation, and coupling between them is very small. So I treat this a molecule, if I consider both, one is 119, other is 117, a coupled AX spin system. 119 can couple to tin 117, it forms AX spin system. Where let us see, AX spin system should give 2 doublets, doublet for A and doublet for X. Okay. In this possibility, there are 2 such possibilities like this. This is 119, this is 117, possible. That is one molecule. Other molecule, this is 117, this is 119. That is also possible. There are 2 such possibilities. So that means 2 AX spin systems. 2 AX spin system means how many lines you expect? 8 peaks. 2 at you get for tin 119, 4 you get for tin 119, 4 for tin 117. For each of these AX, 2 lines will be there for this one from one AX, another 2 lines from other AX, similarly 4 lines here for 117. And 117 in the detect you get 4 peaks. We are detecting 119. So, of the 2 AX spin system, 4 peaks should be able to, we should be able to see that here. Okay. And this is what it is. This already we have assigned. For this possibility, I said one is A, other is B. I have written this is A, this is B. So, this is one doublet. Because of, I said the AX spin system, it has to be a doublet, one doublet. Other doublet, where it is going? CNET 117, tin 117 resonance. We are not saying that. 8.3 megahertz away. Okay. What about the other one? This possibility is another doublet. Equal intensity. Exactly from the center you can see. So, 4 peaks we have assigned. Remaining 4 peaks, if you want to see, go to tin 117 NMR. Fine. So, one doublet is detected for this, other with this thing. What happened to other peaks of 4 peaks of AX? They are seen at tin 117. I told you. Now, what is the possibility 3? Both can be 119. Why we have to take this 117, this 119? Why not both can be 119? That is definite possibility. In which case, it forms a AX spin system. Okay. One AX spin system. And there exists a coupling between this and this. And only one such possibility. So, this there is a molecule, possibility 3, both tin could be 119. Now, that possibility should give rise to 2 doublets symmetrically placed for each of these 2 strong peaks, A and B. So, we analyze this, we analyze 4 peaks here. Now, what is left over? This is one doublet, this is another doublet, which is coming because of this one. Okay, so we could easily make assign these 4 peaks. Doublets coming because of coupling with is a situation where both are tin 119. Each forms a AX spin system, gives doublets at the chemical state of both A and B. Another possibility, this is 119, this is carbon 13. This is 119, this is carbon 13. There can be a coupling between them. Okay. In which case, again it forms 2 AX spin system. And 4 sets of doublets you get. 2 doublets at 119. And where do you get the other set of doublets? 2 doublets. Carbon 13, 1, that NMR. So, 2 doublets are seen, each for the chemical state of A and B. And this we have analyzed, this we have assigned, this we have assigned, and these are the 4 peaks. Very weak. So, with that also we could get 4 peaks. Each of them is giving 2 peaks doublets. That's done. Okay, next. What happened to other set of 2 doublets? They are seen at the 13C resonance. What is the last possibility? Not last, fifth possibility. Both could be 117. You don't see that in the tin 119 NMR because you have to go to tin 117 resonance, which is 8.3 megahertz away. Then you will see all those peaks. What is the other possibility? This is 117, this is carbon 13, this is 117, this is carbon 13. That's also possible. Okay, that you will see again in tin 117. Fantastic. You see, so beautiful, simple molecule. Each peak can be assigned. Okay, there are looking at varieties of possible isotopomers. We could assign every peak is genuine. Okay, next we will go to the example of a lithium NMR. Lithium NMR is consider this molecule. We can see lithium 31P 13C all NMR spectrum of this molecule. This is a lithium diphenyl phosphidine dimer. If you look at the lithium NMR here, I am going to get a triplet. Why we are getting a triplet? See, lithium is coupled to phosphorus equivalent. Both are chemically equivalent, equally coupled to 2 phosphorus. As a consequence, it's a triplet. That we know. When there are 2 equivalent spins coupled, it will be a triplet. And this separation gives me lithium phosphorus coupling. Very easy. And if I look for the carbon 13 NMR of it with proton decoupling, you must get only phosphorus carbon coupling. I am decoupling proton. I am looking at carbon. And very two carbons are close by. One is direct bonded to it's a ipso carbon, other is this one. These are all far away. Other carbons here. So we will expect at least look at two carbons. One is ipso carbon and ortho carbon. Each of them is a triplet. Why? JPP is very large, 2 carbon 13 forms a ABX spin system, and coupling between them is AB is there, and it is called an ABX spectrum, and we are looking at the X part of AB. So this is what is happening. As a consequence, each of them is going to be a triplet. Okay, JPP is so large, about 200 hertz. As a consequence, we get triplet for each of them, and 13C appears as a triplet because of this. All right, and of course remember we are breaking the coupling between proton here with carbon. We are going to get only phosphorus and coupling and lithium coupling, both could be, we could see both of them. Selenium 77 NMR you can think of. What is a selenium 77 NMR? It is a spin-off nuclei. Natural abundance is only 7.6%. Let us look at this molecule. How many peaks we can expect for this? It is a very big molecule. This is a big name for it. And we can see 1 bond selenium phosphorus coupling. And we can say 1, 2, 3, 4 bond selenium phosphorus coupling also. Both are possible. Simply record the spectrum of it with proton decoupling. You are going to get 2 peaks. Okay. What are these 2 peaks coming from? You can measure it. This is coming because of 1 bond selenium phosphorus coupling. Why 2 peaks? Actually there is a symmetry. Only one selenium is you have to consider. But there is a phosphorus coupling 1 bond that makes it a doublet. So that's why this is a 1 bond selenium phosphorus coupling. But each of them is further, there is a multiplicity. Why is it coming? It is coming because of selenium coupling to phosphorus, which is 4 bonds away. And why there are no proton couplings? You have broken the coupling between selenium and phosphorus. It's a decoupled spectrum. All right. So as a consequence, we see only that. What about the analysis of the selenium spectrum of iodoselenophene? If you look at it, we look at the simple molecule. We analyze the proton spectrum of it. If you please remember, when I analyze the proton spectra, there is only one selenium. One selenium, there is a actually 2 bond selenium proton coupling. It will be a doublet. And there is also another proton coupled to selenium. Each line of the doublet is going to be another doublet. So doublet of doublet. And further what is happening is each line of the doublet is split into 3 bond proton selenium coupling. This is iodine. 3 bond selenium proton coupling. This is 1 doublet. You see, 1 doublet, 1 doublet, 1 doublet. Each of these 4 lines is split into further doublet. So it is going to be doublet of doublets. DDD we are going to get. And this is the pattern you are going to get. And from the separation, you can measure 1 bond selenium proton coupling and 3 bond selenium proton coupling. And similarly, we can look at the selenium NMR of this molecule. What is that you are going to get if you look at the selenium NMR of this molecule? See, this is the structure. It is what is called AXB4 spin system. We are looking at the selenium X part of it. So these 4 equivalent fluorine, this is different fluorine. These 4 equivalent fluorine, this thing is split into a quintet, and then each line of the quintet is split into a doublet because of this coupling. You understand? We are looking at selenium. These 4 equivalent fluorine splits this into a quintet, and then each line of the quintet is split into another doublet because of coupling with another fluorine. And this is how it is. This is a pentet of doublet. I say pentet because this coupling is larger. You see, JXP is larger than this. We always have to take the larger coupling. So this is how it is. This is for center, and then this is one peak and other peak coming because of. See, from the center, there is going to be, like I showed you, this is a 5 peak pentet, and each of these is split into a doublet like this. You see, as a consequence, it is going to be pentet of doublets, and this separation gives you this coupling. Of course, you can also do Xenon NMR. Xenon has spin 3/2, abundance is 21%. Xenon 129, spin is half, abundance is 26.4%. There are 7 other isotopes, we don't need to worry. But look at this Xenon NMR spectrum of CA3C in this molecule. 1 bond xenon fluorine coupling is there. Xenon is directly bonded to fluorine. This is spin-off nuclei. Xenon 129 if you do, it is going to be 6000 Hertz. You see, large coupling. And each of them is further split because of nitrogen 14 coupling of intensity 1:1 should be there. Okay. So, this is Xenon 14 coupling of 300 Hertz. And in case what happens if interestingly, if you are going to label the system, carbon 13 is labeled, then in which case what will happen? This xenon coupling is there. This is xenon nitrogen 14 coupling, and each of them is coupled because each line of this triplet, a doublet of 3 lines of equal triplet is further split into a doublet because of carbon coupling. See, this is 6000 Hertz, 300 Hertz, this is 73 Hertz, and this is what the pattern you are going to get. And if you look at the nitrogen 14 NMR of this molecule, it is very broad because of nitrogen 14 relaxation. All these things what happen. Of course, this is a platinum NMR. Similarly, you can do that. There is no issue. Platinum chlorine, if you look at it, chlorine has different types of isotopomer. Like we saw in PCl3, varieties of isotopomers are present. Each of them is going to give you a peak. Okay. This is the situation where all chlorine are 35, one is 35, others of 37, like that. All isotopes you can consider for this molecule, and you get different peaks, 5 to 6 peaks. All peaks intensity can be calculated based on the population of the distribution of the different type of isomers. Same thing you can do for bromine. That means all when the halogens are substituted, this type of isotopic effect is going to be dominant. And the last example is germanium NMR. Spin is 9/2, and when it is coupled to proton, germanium, it is going to be a doublet. Obviously, it is a doublet. GEH. I am not worried about the pH3 part. If it is take GEH3, it has to be a quartet. We got it. pH part, we are not worried about the coupling. That may be far away. So, this is germanium. It is spin by 9/2, quadrupolar spin coupled to spin half nuclei. And we can analyze that and get the coupling information. This is a germanium proton coupling of 90 Hertz, about 100, close to 98 Hertz. So, this is how we can analyze germanium NMR. We saw xenon NMR, etc. Lot of examples we took today. So, in summary, I told you today in this class we have taken several other examples of different nuclei like selenium, xenon, platinum, and germanium. Various examples we do, and we and nitrogen 15, nitrogen 14 NMR. Several examples we took, and we could easily assign based on the multiplicity pattern and get all the coupling information. So, with this, I have given you fairly an idea about analysis of the spectra of varieties of heteronuclei, which you commonly come across in material chemistry, biological studies, bio-NMR, or simple organic chemistry, organic molecules, where you could think of proton, carbon, nitrogen 15, phosphorus, fluorine, varieties of nuclei. So, at least you got a fairly idea when you have a different nuclei, spin-off coupled to spin-off, spin-off coupled to spin, the quadrupolar spin. When you are detecting the quadrupolar spin which is coupled to spin-off, or which is coupled to spin-1, or other quadrupolar spin, what is the pattern you are going to get? And how you can interpret it looking at the pattern, how we can get the couplings. And we saw over the period, the couplings could be enormous. In, for example, xenon proton coupling was 6000 Hertz. Coupling strength can be different, enormously different. It could be few Hertz to several thousands of Hertz. So, all those things we observed when we studied different nuclei. So, I think you got a fairly idea about analyze the 1D spectra of not only proton, carbon, varieties of abundant and dilute spins, both spin off and quadrupolar spin. So, further we can continue, but lot of work nuclei there, lot of isotopes are there, which you can continue and do it. There is no issue for that, but I cannot keep on covering all the nuclei. I took several examples for this. I am going to stop here. From the next class, we will go to a completely a different topic. Thank you very much.